Hello, everybody. In this video, we are going to be talking about integer programming problems. So the different kinds of integer programming problems, which we'll talk about in a second. This video is not intended to be an introduction to integer programming as a something for master students. So this is more simple integer programming problems for undergraduate business students. That's the context for this particular video. We've seen linear programming problems before, and the linear programming problem is a problem where all variables are restricted to be linear variables. But an integer programming problem or an all integer linear programming problem is one where all variables are restricted to be integers. Now, we've seen examples of this before when we were looking at product mix problems. When you have to make a certain number of chairs and tables, the variables had to be integers. But as I said in those contexts, that the numbers are such that the results end up being integers. But what if the results don't end up being integers automatically? So a linear program where you take an all integer linear program and you drop the integer requirement, that's called the linear programming relaxation. So you're relaxing the condition that all your variables have to be integers. You're letting them be continuous variables, and that's called the LP relaxation. If only a subset of the variables are restricted to be integers and the rest of the variables can take any values in any linear values, then it's called a mixed integer linear program, or MILP. Now, binary variables are variables that are restricted to be zeros or ones, and binary variables are very commonly used in integer linear programming problems, and we will see a few in this video. So they are binary because they can only take two values, so it's called a binary integer linear program. But you can have integers that take other values. So here's a simple example. So Eastbourne Realty has $2 million for a new rental property. Eastbourne wants to invest townhouses and apartment buildings. Those are the two types of constructions that it wants to make. Now, each townhouse can be purchased for $282,000, and there are 5 available. Each apartment building can be purchased for $400,000, and the developer will construct as many as Eastbourne wants to purchase. So there are no restrictions on the number of apartment buildings that they can get. Now, Eastbourne property manager can devote up to 140 hours per month on these properties. Each townhouse requires 4 hours, and each apartment building requires 40 hours a month of management. The annual cash flow deducting mortgage payments and operating expenses is expected to be $10,000 per townhouse and $15,000 per apartment building. So that's how much profit you can expect to make from each of these. Of course, there are other things that come up, but this is the average value. Now, Eastbourne's owners want to figure out how many townhouses and how many apartment buildings they should build to maximize the annual cash flow. Now, if we forget about the fact that the number of townhouses and number of apartment buildings have to be integers, they have to be obvious. We cannot have half an apartment building. We can have, or half a townhouse for that matter. So you need them to be integers. Now, if you forget about the fact that they're integers, then you can easily formulate this problem as a linear programming problem and solve it. One of the things that the textbook does go over a graphical solution for these integer programming problems. I'm not going to go over the graphical solution. We'll just use Excel for solutions. Right? So the two decision variables in this case are the number of townhouses to purchase, and A will be the number of apartment buildings to purchase. The objective function, they have reduced thousands of dollars. So we could say 10,000 times T plus 15,000 times A, or you can say 10T and 15A. It really doesn't matter. This is the total profit that you expect, a monthly profit that you expect, or cash flow as they call it. Now the constraints must be, so let's look at the constraints. First is the price of a townhouse and the price of an apartment building, and we have $2 million available. So again, this is written in thousands of dollars. So 282,000 times T plus 400,000 times A is less than or equal to $2 million. 2 million is 2,000 thousands, obviously. So that's the first constraint. The second constraint is the manager's time. A manager has 140 hours available, so the person that they've hired, they can denote 140 hours a month for management. Each townhouse takes 4 hours of management, and each apartment building will take 40 hours of management. And there are only 5 townhouses available in total. So T has to be less than or equal to 5. So these are the constraints that we have, and of course T and A must be non-negative and they must be integers, right? Now, if you put this problem into Excel, let's do that. Let's do that quickly. So you have townhouses and apartment buildings, apartments, right? So those are 2 variables, T and A. You have decision variables, right? So these are our decision variables right here. Objective. Now, the formulation, obviously, in the textbook, it does everything in thousands of dollars. I'm just going to put it in dollars. $10,000 and $15,000 from apartments. That's how much profit you make, of course. Let's not forget the left-hand side and the right-hand side of the constraints. Let's have those columns ready. And then the first constraint is the budget. The budget, so it's $282,000 per townhouse. That's how much the townhouses are going for, and $400,000 for apartment buildings. And this has to be less than or equal to $2 million. It's $2 million. That's the first constraint. So the second one is the time, manager's time. The manager's time constraint. So if you look at that, manager needs to spend 4 hours on townhouses and per month and 40 hours on apartments per month, and this has to be less than or equal to 140, which is the total number of hours available for the manager. And then finally we have the maximum number of townhouses. Now, there's no maximum limit on the apartments because we know that the builder will build as many apartment buildings as the construction company wants. So maximum number of townhouses is 5, right? We have all less than or equal to constraints. So I can write my product function. Let me write it here for my objective. Oops. So the decision variables have to be absolute references. The objective coefficients should not. So no dollar signs for the objective coefficient. Remember that. There you go. So my problem is right here. Right. So I'm going to put this into solver. So the objective is to maximize. So I'm going to leave it as maximize. Decision variables are these 2. So we have 3 less than or equal to constraints. I'm going to choose all 3. On the right hand side of the 3 less than or equal to constraints. Okay. Right. So make a constraints variable non-negative. So we are not imposing the integer constraint just yet. So if I solve this problem like this, okay, solver found a solution. But you can notice that this is obviously a problem. So even if I just go down to 2 decimals, obviously. 2.48 and 3.25. So you want to build 3.25 apartment buildings and 2.48 townhouses, which doesn't make sense. I mean, mathematically it makes sense. That's the point of intersection of these lines. So mathematically it makes sense, but in reality it doesn't make sense. So what do we do? How do we manage this? So the way you do it is you impose the integer constraint and you say, tell Excel that these variables have to be integers, right? In reality, if you look at the graphical solution, this will be a feasible region. And if you look at the endpoints, you'll turn out that this is the endpoint that will give you the maximum value, 2.48 and 3.25. So that's the solution that gives you the maximum value, right? But that's the problem. Now, the feasible region tells you these are all the potential values that the decision variables can take. These are all the potential values that the decision variables can take and still satisfy all the constraints. But that is actually not true, because we specifically need the decision variables to be integers. So in fact, if you look at the feasible region should actually be just these blue points, because within this feasible region, these are the blue dots. These blue dots are the only values where both townhouses and apartment buildings are integers. So this is 1, 1, 1, 2, 1, 3, 1, 4, or 1, 2. So these are all the blue dots are all the values where the decision variables are integers. Now, in this case, these are not a lot. In fact, I think they're probably like 1, 2, 3, about 3 times 5, so about 15 of them. So you could literally list these 15 values, plug them into the objective function and figure out what the optimal solution is. But in real life, when you do integer programming problems, you could end up with like, a million of these values, or 100 million of these values. So I have done some research with some blood bank inventory management, where when you impose integer constraints, it could be millions of these variables, and they're not just 2 axes, they are multiple axes, so it can get really complicated. In this case, it's pretty straightforward. So if you look at all of those points, you'll find that the optimal solution is actually 4, 2, that is buy 4 townhouses and buy 2 apartment buildings to maximize the profit that you can make. But this is what you do if you're looking through a graphical solution. And like I said, we're not going to go over the graphical solution. The way you do it in Excel is, Excel has this special feature. So if I go back to Solver, so when you add constraints, you can add some extra constraints. If I click on add, I would say that my decision variables, both of my decision variables here, they have to be integers. And in Excel, you can say that. So you can add that as a constraint. So you choose your decision variables that need to be integers. You click on this, and here you have these 2 options, right? int. So if you click on int, it says integer here. You cannot type in integer and expect it to work. You have to go down this list and you have to pick the int. Only then will it work. By saying int, you're saying that these decision variables have to be integers. Similarly, bin stands for binary. So if your decision variables have to be 0s and 1s only, then you pick binary. Now, diff is a different kind of binary where you want your decision variables to be +1 or -1, but we are not going to encounter any problems where you're going to do the diff variable. Those are very special cases. We'll be using int and binary. So int if you want them to be integers, as in this case, or bin if you want them to be binary, right? So I'm going to click on integer and I'm going to click OK, which means that we have added an extra constraint saying that my 2 decision variables actually have to be integers. I'm going to click on solve. It's going to take a couple of seconds, especially because I'm on a Mac. The solver is not as good as the one on Windows. On Windows, it's much faster than this, but in this case, it didn't take too long either. Okay, so our final solution is 4, 2, like we saw with the graphical solution, right? Okay, so buy 4 townhouses and buy 2 apartment buildings, and you will make a monthly profit of $70,000. That's the expectation, right? Okay, so that's how you do it. You just add an extra constraint saying that the variables have to be integers. Okay, that's the first problem. So this video is already 15 minutes long, so I was going to do another example. I will post that as a different video. I'll see you all in the next video.